We're going to start into flow sensors. And luckily I had this guy over there. This is our backup for our file server. So I just brought it in, and so I can still access our PowerPoints.
Don't lose that.
No, I got to take it back. Melton sent me an email saying he's going to be late.
Well,
Not an email. He sent me a text.
Eric told me in that class.
And Eric's going to be late too.
He said he would be late.
Yeah, he's got a interview, I think, with Flexengate. I think Gas Stump or Flexengate. It's one of those companies that hire our students. So he said he would be late.
He really does.
Thank goodness I've got one. Okay, so sensors, flow meters, we know what a sensor is, right? So a sensor is a device that converts a physical stimulus into an electrical equivalent. And these are the sensors we've gone over so far. We've gone over position, weight, pressure, temperature, light. We've gone through liquid level, motion. We've gone through proximity, and then this is basically where we're going to end up. If we have time, we might look at these guys right here, which is when we start adding vision systems. What we're going to do here is talk about flow rate. Unfortunately, I don't have any flow sensors available to us. I guess I should have went over to the Fluid Power Lab and see if I could find them. So flow, what do? You measure flow you measure flow in this. What type of flow do y'all measure?
Well,
in here, not there. What type of flow do y'all measure?
we measure current.
Current. That's exactly what flow is. So what you're doing when you measure flow, you've got a flow meter. You're using a flow meter, and that's what your ammeter is. It's measuring the flow of current. So we use flow all the time. Here, mainly, we're going to be talking about fluids. Now, what is a fluid?
A fluid is something that's not solid. No.
Well, basically, a fluid is
water, air.
Yeah, it's something that doesn't have a fixed. So a fluid does not have a fixed shape. A fluid is anything that takes the shape of whatever container it's in. So usually when I teach it, my granddaughter, she's not in it. My granddaughter, she's 9. She has a tendency to get in cliques, and she got into making slime. And they don't tell it how many things of slime we made. But slime is technically a fluid, because if you take that slime and you put it on this table, it'll just spread out. If you put it inside a container, it'll just take the shape of the container. It would be more on what we call a slurry. But even solids can be fluids. Think flour, cooking, the flour that you cook with. What does it do? It takes the shape of whatever and it flows freely. So if you put flour and you tilt it like that, it just does what? It just builds. So flour is a fluid. Anything that's ground really, really fine and has the ability to take the shape is fluid. Now, normally when we talk about fluid power, we're talking about liquids, the use of liquids and the use of gases. In fact, that's all we're talking about. So we wouldn't use flour, cooking flour, in a system to create power, right? Does that make sense? So first of all, we need to understand what flow rates are. We have our SI units, and I should be uppercase, by the way. These are our international standard units. We have, of course, in there for volume. So when we talk about flow, we're talking about volume, right? We're not talking about, we're talking about moving so much volume past a certain point in a certain, in a time. That's what flow is. So gallons, when we talk about gallons, we're talking about volume, right? And volume is something that occupies not only width, but also height and depth, right? You understand that? So we're talking about volume. So standard units, we use liters. Or another thing for area. So cubic, that would be volume per second. Cubic centimeters per second. Cubic meters per second. Cubic centimeters per second. These would be what we use in what we call the international standard unit. Inside U.S. customary, we're either going to use gallons per minute or we're going to use cubic feet per second. Right? Does that make sense?
Yes.
Okay, when we talk about cubic, we're talking about a volume, right? Everybody okay? And of course, we've looked at this several times. So normally, to sense flow, we have some type of what? Sensing element, and I should change that, take that flow off and put what? I mean, take pressure off and put what? This should actually be flow.
Well, it is under pressure.
Well, it creates pressure, but we're not, the indicator or the sensor that we've got is not measuring pressure, it's measuring flow. Yeah, the sensor. So what we do here, we have some type of sensing element. Now you got to understand, how do you measure current? True current with an ammeter. We're not talking about a clamp-on. A clamp-on ammeter is not measuring current. It's measuring the strength of a magnetic field, which is proportional to current, right? So we call them clamp-on ammeters, but technically they're not measuring amps directly, they're measuring indirectly. If I want to measure amps or the flow of electricity directly, then I've got to put my sensing element in series with the flow. So it's got to flow what? Through the sensor, right? You understand that? And we'll see when we look at some of these flow gauges where you can actually see where the fluid flows through the thing, and then somehow we pick that what we measure that flow. That make sense?
I think it would have to.
It would. So we have to measure flow, we have to get in series, or we have to make the fluid flow through the sensing element. Everybody okay? And then we flow that through the sensing element, and then if we're gonna have a sensor, we'll have a transducer. And what's a transducer? What is a transducer? Most of our sensors can be transducers, but it doesn't necessarily have to. So what's a transducer? We already talked about that.
It has to control.
It converts one form of energy into another form, right? You understand? So out there at Alabama Power, when they've got them big old generators, they're taking water on their dam. They're taking water energy and converting it over to electric energy. So technically, a generator is a what? It's a transducer. So we have sensors, and then we have a transducer. We have a lot more devices that would fall into the category of a transducer than there would be a sensor. So basically, and a lot of people try to want y'all to understand that. So it's kind of like saying a Ford is a car, but a car don't have to be a Ford, right? You understand that? So most of our sensors are actually transducers, but we can't say sensors and transducers are the same. Everybody understand that? And then, of course, if we're going to do electrical, then we're going to have to take this and we're going to have to convert it over to electrical, and then we'll come up here and we'll do what? Then we'll actually get it into the situation that we want to get it into. Everybody okay? These are actually flow meters, so these are basically flow gauges. And this is one method we can do it. All of these are actually somehow it's taking the flow and converting it over to some type of maybe mechanical signal or electrical signal for the meter. You can see what these gauges are measuring.
Most of those gauges are adjustable. Can you adjust flow to them with that?
No, these are not flow control valves. These are flow meters. All are flow sensors. All these things is written. All this measuring is the flow gauge. Now they might combine a flow control valve with a flow meter, right? You understand? But that's actually two different devices that's doing two different functions. Are we okay?
Okay.
So these are a different type of flow sensing. So this is the actual sensing element. How do we sense that? We use differential pressure. We have what we call an orifice, Ventura, and a Piot static. We have a rotometer. We have a spring tension turbine, paddle wheel vane, magnetic flow meter, and then ultrasonic flow. Now, not meters, sensors. I need to get this straight. These are the elements that senses the flow. Everybody understand? Okay. So this is what we call a spring and piston. So what we have on a spring and piston, we have a calibrated spring. And then when the flow comes through, it does what? Pushes against this piston, causes this right here to move. And then what we do is we either have a scale on here that indicates the motion. Now what this is, I don't know if you can see it. I think this is actually a magnet. So when we move this, then the magnet is going to cause, or whatever we're out there sensing. It could be, if we want to do it electrically, then our transducer would be like a Hall effect, right? You understand? If we wanted to do it digitally, then we might have a reed switch out there. And then when the reed switch would hit a certain point, it would actually give us a signal that the flow is okay or not okay, right? Now a reed switch, of course, is digital. Everybody understands that. Hall effects can either be digital or they can be analog. So what does a Hall effect sensor do? Well, it senses the magnetic field, or it can actually measure the strength, right? You understand? So we have an analog Hall effect, which would measure the strength. And then we have a digital Hall effect that actually trips at a certain strength of the magnetic field. Are we okay? Pretty straightforward how this thing works. Any question on that? This is what we call an orifice plate. So basically what happens, we squeeze the thing together. So what we end up with when we hit this orifice plate. Now the problem is that these guys here, we're going to have a pressure drop across some of our flow systems. Right? You understand? In fact, almost all of them will have some type of pressure drop. If I come up here and it's coming over here and push it against this piston right here, then we're going to lose some of our pressure going through the piston. And that's the way these things work. So normally most of these, in fact, I think all of them, we work on we create a pressure drop. You understand? But it's not going to be very much. So over here we might have 100 psi, and over here we might have 95 psi, right? And we lose that pressure going. Anytime you send flow through an opposition, you lose pressure. And we see that all the time in electricity. Anytime we send current flow through resistance, we lose what? We lose pressure, right? We have what we call a voltage drop. Well, here we would lose pressure inside our system, but it's not going to be much. But it's something we have to sacrifice to sense what? To sense flow. Account for, right? So Gary was involved on designing hydraulic cylinders, or trying to do the math to order hydraulic cylinders. And that's something of things you gotta assume that any device that you send, that even the piping. So our wires our conductors have resistance. So that means every wire has a voltage drop, which we have to compensate for to get the right voltage or push to the load, right? You understand? Even the piping. So if I put a fluid through a pipe, then that pipe is going to have a certain amount of opposition to the flow of that fluid, just friction along the outside of the pipe. So you're right. That if you was an engineer, that's one thing you would have to do. So if I needed 100 psi at a certain flow rate at my actuator, then I'm going to have more. I'm going to have to calculate what pressure I actually need on the input of the system, right, to get that pressure out, regulate the flow. So that would be engineering. Odds are you don't have to worry about that. It's just that if you're a technician, you need to, if you're going to replace one of these things, you need to get the part number and look at what they call the pressure differential and the port sizes, and make sure you get one that's got equivalent port sizes, right, and then flow rate. So you can see that hopefully the way this thing works. So here comes this guy flying through here. It hits this orifice. It's going to build up pressure on this side, and the pressure over this is going to be less. Well, the pressure drop we have through the orifice is going to be directly proportional to the flow, right? It's just like we say what? I is equal to V over R. So it's directly proportional to the opposition, right? You understand that? So we deliberately created a resistance or an opposition. Then what we do is we have a tap on each side, and we measure, all we have to do is get the differential between what? This pressure and that pressure. So I could run this into a differential pressure sensor like the diaphragm that we looked at. I could bring one pressure on one side. I could put the low pressure on the cavity, high pressure coming in, and then the output of that sensor would be what? It would be proportional to flow rate. You understand what I'm saying? Yeah. Pretty neat. This guy creates a pretty good deal of opposition though. So, but it's used, and you can see it basically just looks like a washer, right? Just stuck in here. And then these would be the two differential.
Pretty small in that picture. That looks smaller compared to the. Yeah. Well, I don't know. I guess it's 4.
Yeah, and but you can see the two pressure ports right here. So this would be your two pressure. One's on your high pressure side. One's on your low pressure side. And then you just measure what? The differential pressure. Are we okay? This is probably one of the most popular ones used. This has a less opposition than the orifice. This is a little harder to use. This works on the principle of any time the flow rate goes up, the pressure goes down, right? You understand? That's the way airplanes work. So what happens is the wing is curved. So when the air comes up and hits that thing and goes over the top, it's got to go over that hump. So it's got further to travel, right? So what? The speed goes up. And then on the bottom, it goes straight across the bottom of the wing, and the pressure is the same. It creates
that speeds it up.
Yes. And if it speeds it up, the pressure goes down. You see these all over the place. This is the most popular. By the way, this is what we use on both of our manufacturing lines to generate a vacuum. It's just that we don't have this port 2, we have port 1. So what happens is when this air comes flying through there, it creates low pressure and causes the pressure to go down, right? You understand? So over there on our manufacturing line, we don't have any vacuum pumps. What we do is we use the flow of the air that we got, we send it to a Ventura like this, and then that pressure generates. Anybody's got a pressure washer. Most pressure washer has this thing. So you can come out there and you can put a tank on the outside, right? You understand? And even though that pressure is coming through there, why don't it come out there? Well, they send it to a Ventura, which creates low pressure, right? And what does it literally do? It literally takes your soap or whatever you're washing with and sucks it into the stream. And that's so if you got a pressure washer, most pressure washers has a Ventura inside there, so you can add things, right? Like soap and stuff like that.
An old electrical engineer guy, he showed me how to siphon gas with an air valve. You ever seen it? You stick the hose in the tank and just blow the air across the end of the hose and it'll suck it out.
Yeah, because that's what you're doing in same principle. You got high pressure, you got fast flow across the end of that, and you create a vacuum.
Yeah, I've seen it work.
I've never did that. That's the first I've heard. That's a good idea.
Well, you don't.
So these things can be extremely big, or they can be small. And you can see on this one, you can see the two pressure ports. And what we would do is we would measure the differential pressure, and the differential pressure would be proportional to speed, right? You understand that? So the way our ammeter works, it works on exactly the same principle. So what we do on an ammeter is we send our current through a resistor. So what we're doing deliberately is we're increasing. So we call it a shunt because it has almost no resistance at all. Your high current shunt might have like 100 milliohms. And then what we do is we put our current through here. This is inside the meter, and then we measure the voltage drop across the shunt. So we measure differential, but your meter don't display it as V, it displays it as what? I. So if it's 100 milliohms, I'm sorry, 100 milliohms. Then 5 amps would be 5 times 100, so it's going to be 500 millivolts, right? You understand that? And then 500 millivolts, I bring that into my meter. Instead of saying 500 millivolts, I just move the decimal point over and say 5 amps. So this is the way your meter works. So your meter's working on exactly the same principle. What does it do? It creates a difference in potential. So we put flow through an opposition, and then it creates a difference in pressure. So this is the way your ammeter works. Exactly the way. Now your milliamp scale is probably going to have like a 100 ohm resistor in there, but you got to remember that's milliamps, right? So even if 1 milliamp flows to a 100 ohm resistor, it's going to drop 100 millivolts, which is not going to be enough problem. So, and you can measure this. You can take your meter and put it on amps, and then put it across the 10 amp thing, and take another ohm meter and put it across there, and you can measure that resistance.
I remember you taking one apart, showing us.
Yeah, I showed you the shunt, and that's all it usually is. It's just a piece of wire, but it's calibrated. It's made so it has a really precise resistance. There's a lot of companies. You walk into a company, they'll have an ammeter over here, and it's displaying 1,000 amps. Well, I don't bring that up and make it flow through the meter. I put a shunt out there somewhere, right? You understand? And I make the current flow through the shunt, and my meter goes across the shunt. So my meter might be seeing 50 millivolts full scale, right? You understand that? Or 100 millivolts full scale. And it's up here saying 1,000 amps. But actually, it's just measuring the voltage drop across the water shunt somewhere. So we do the same thing. This is the way your ammeter works. So if I'm going to measure amps, we do it exactly the same way we do here. We create a precise differential or pressure drop, and then we measure the pressure drop, and it's going to be what? Directly proportional to this. Now you can see the Ventura would have less opposition than the what? So it'd have than the orifice plate. The other thing that we use is they call it a PDOT static. This is what airplanes use. Measure their wind, measure their speed. Pretty neat. So what we do is we force flow into one sensor, and then we compare that to the static pressure. And that way we can measure flow. So this is the way airplanes measure airspeed. What they do with the static pressure is, as the plane, and it's really interesting how it works, but it gives you accurate reading no matter what altitude you're at, because your static reference so your static reference changes with altitude, right? You understand? So if I go up, my static pressure goes down, and my PDOT pressure goes down for the same speed. So and the static sensors on the airplane are actually on the side of the plane. So they're down the tube of the plane. Well, it does, but PDOT tubes on airplanes have heaters on them. So they're heated.
That's what I was thinking.
Because if you don't heat them,
30,000 feet, it's cold.
It's cold, right? So they have heaters on them. We had this is a true story. We had a guy from Texas. In fact, we called him Tex, and he was a great guy. But we was over at the NCO club, and they had these candles on the table. And anybody that could put their hand, it was inside this glass container. If you could put your hand over the top of that glass container and put the candle out, everybody would buy you drinks. So Tex did that, and it burned his hand real bad. And when he got home, he told his wife that he grabbed onto a PDOT tube. Because they'd get out there, and they had to put covers on them all the time because dirt divers like to build nests in our PDOT tubes. So that was one of the things you covered up. And the static tubes on the side, you had plugs you would put in those when the plane was on the ground. And
what part is it exposed?
The PDOT tube is exposed. So if you ever look at a plane, it's usually under the nose. If you ever look at an airplane, and it's usually around the nose. Probably on these little small planes, if that's propeller driven, it won't be in the propeller. It'll be probably out on the wings. Our planes, though,
But it's a little curved.
Yeah, it's curved tube.
Yeah.
Comes out and points straight toward the air, points straight toward this way. Yeah. And then, so you'd come up here on our planes, sorry.
These fly little things.
Yeah, but they were on, I think small planes, they were out on the wing, especially propeller, because you didn't want them to get into the prop. But yeah, you'll see a little thing coming out and it'll be like this.
Yes.
And then usually it's pointed like that. And then it's pointed toward the airstream. And then if you look down the side of the plane, you're going to see little holes in the side of the plane. Well, the holes in the side of the plane are the static. And why they put them on the side of the plane is so it senses when the plane turns. So if you turn, this guy would have more pressure, the guy on this side would have less pressure, and they sum them together. So the static pressure would be the same no matter how they are. So PDOT tubes to work, you got to have static, so you got to have something that you compare it against, right? You understand? So you compare it over here to a static pressure, then you put the pressure, the flow into that. So that would create a pressure, and then we'd have some type of pressure sensor that would take that. And so what we're doing, it's just like on a lot of our sensors. We have a sensing element, and then we might have another sensor that does what? That actually converts it to electrical. Are we okay? So PDOT static, PDOT tubes. Normally we said PDOT static because you can't have a PDOT tube without a what? Static. That makes sense? These are rotometers. And so basically they work off of pressure too. So we come up here, we put flow through the thing, it tapers down, right? You understand? The flow changes, and then this thing right here would just rise up with gravity, and then you could read it off the side or have some type of unit over here that would convert this. So this could be a magnet, right? You understand? And then we could have holotechs out here, right? You understand that? Or it could just be this and then you just convert a dial. Are we okay?
I've seen that.
Yeah. They're very, very popular on swimming pools. So if you got a big swimming pool and you're going in there and you're looking to see, and that's what we used to do. We used to have a community pool that I was responsible for little things, but they had a flow meter that did this same thing. And that's why you could tell when your filter, your sand was getting clogged up, is you'd look at the flow meter. And if it dropped down below a certain level, then you'd come in and you'd back flush your sand, try to clean it out. But yeah, these guys here are very, very simple. I haven't ever seen them used with an electronic sensor on them, but they could be, right? Because this is the sensing element. All the ones I've seen, they just have a markings on the side. And you just look at the flow. And you look at the markings on the side. So on the side of this tube, this would be, normally this is plastic, clear plastic, and then this would just be on the side, and I would just read the flow directly off that. So I've never seen one that, one of the road meters, I've never seen one that actually outputs an electronic signal, but hopefully you can see, anytime I've got motion, I can electronically sense that motion, right? This is pretty obvious how this works. This is called a vane. This would be very easily converted over to electronics. In fact, that's what this is doing. So what happens here? It comes up, it's got a vane sticking down in the flow, the flow hits it. This is like every kid that I know of has done this in the way. We've been driving along the road, the window out, when they put their arm out there. Well, that's what this is exactly what you're doing. And we used to fly our hands over there. Everybody probably did. So this just puts a vane in there. When the flow comes in, what does it do? It moves the vane. Then here they've got it connected to a potentiometer. And so when the vane moves, it changes the potentiometer, which would give us a lot. It would give us an electrical output that indicates the flow. Of course, we'd have to know how to do the transfer function, right? So we'd have to know what voltage we get out relative to flow. And of course, that would probably be in the specifications for the guy. Everybody okay on this? Pretty straightforward. A vane, and this is really, really popular. The one we had on our hydraulic system over there was this guy right here. So we did have flow indicators on our hydraulics trainers.
Quick question on that other one. That dampening vane, is that to keep it from fluttering?
Yeah, and in the flow, if you got fluttering in the flow, then what's going to happen is this guy right here is full of liquid, right? You understand? And then it's got a little old tiny trough coming through it. So that's exactly what it is. That's a really good point. A lot of fluids, when we're running with pumps and when we're running with especially pneumatics and stuff like that, pneumatics or fluids can have a fluctuation to it. And of course, that's why on a lot of our meters, I don't know if we can see them on these meters, but a lot of your pressure meters have that gel inside of them to do what? To dampen it. And what it does, it takes out that fluctuation, which could be a lot of stress on your vane and everything. That vane was sitting there doing that, right? And it would be a lot of stress. This is pretty obvious how it works. This is paddle wheel. And this shows, this is done electronically. So what we have is they have magnets on each tip of they don't show it here, but we have magnets on each tip, right? You understand? And we have like a Hall effect sensor over there. And when it's spinning, every blade would give us a pulse, and it would work almost just like an encoder. And then we could do the speed of the pulses would tell us the flow rate, right? The paddle wheel, pretty easy to understand. Are we okay? And then I think, no, this is what they call a turbine. Basically it works like a propeller. I mean, most of us as kids has taken a fan and blown into it and made it turn, right? Especially little things. And the things that you use as kids, those paddle wheels, those turbine, that's paddle wheels you use as kids. You ever stuck one of those out of a car window? Once down there flying far. So you put that sucker out the flow window, it really goes. You see those things, they're popular out on graves too. So this works almost a lot like a paddle wheel, where we come in and put a magnet on one blade, right? You understand? And then we have the Hall effect sensor, and every time the magnet comes flying around, it gives us the pulse, and the rate of the pulse is in direct proportion to the speed. Go ahead.
You put a magnet. I was looking at the picture. Oh, okay. That's it. That's the magnet.
Yeah,
no, that's the.
Yeah, this is normally they're like this, and then they'll have something that spreads it out and makes it get to outside the blade. And then the sensing element could actually be back here, right? You understand? It might not be connected directly to the blade. The book that I got this out of is really straightforward, because here they're showing the magnet is actually on the wire. One of the blades is Are we okay? This is another method that's used. There's almost just about every liquid or fluid that we have has some type of electrical characteristics to it, even air. So if air didn't have electrical characteristics, if air was a perfect insulator, we'd never have light. Y'all understand that? Right? So if I can come in and if I move a conductor through a magnetic field, what's it going to do? Well, any conductor or anything that it's got, I need to rephrase that. Anything that's got conductive characteristics, if we move it through a magnetic field, we're going to induce a difference in potential into that. Right? Y'all understand that? I think we showed this thing over here. Y'all seen this thing several times, right? What I do is just take a conductor and move it to a magnetic field, and we see it produces a difference in potential. So if we can measure that difference in potential, and what determines the induced voltage? So what do we need to do to induce a voltage magnetically, or an EMF? How'd the interview go?
Well, pretty good. I got there early.
Huh?
I got there early.
Oh, when they took you ready. What else we need?
Conductor.
Well, yeah, we're gonna say conductor, but basically in this situation, we just need something that's what? Conductive. And then 3, what we have most? Now, of course, these would be set. So these guys, you would have to calibrate them for whatever material you're trying to sense the speed of, right? I understand. Then we generate an electromagnetic field. And then what determines the amount? Strength of the field. Number 2 is the number of conductor loops. We can't do anything about that here. Conductive loops. Of course, here we're just shooting straight line, right? And then number 3 would be what? This is the guy we're doing right here, the what? Speed of the motion. So if I have control of this, then I know the material that's flowing through here, then I can calibrate this. So if I can calibrate, and notice this is an electromagnet. What advantage does the electromagnet have over a regular magnet? Positive permanent magnet. Yeah, we can turn it on and off, or we can control its strength, right? So between the two, we should be able to calibrate this thing. If I can measure the flow of material somehow, then I can calibrate. Now, what advantage does this guy here have over the other ones that we looked at?
What advantage this one has
Yeah.
over which?
All the ones we looked at, every one we looked at so far. This one, 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 right. Well, every one of them can be electronic, so that's a good point, but every one of them could be electronic. Yeah, you could, but this guy right here wouldn't care. Now, this guy right here, this guy right here wouldn't care which direction the flow was. This guy right here would care, so this guy, we couldn't put flow in 2 directions. This guy right here wouldn't care, right? You understand? This guy, if it was a regular propeller, it wouldn't care. This guy would care, though, right? You understand? But the problem is, so if I had a fan and I took my air compressor out and I blow the fan, if I measured the flow, if I measured the pressure on this side and the pressure on that side, it would be different. So every one of these basically create a pressure drop. This guy right here has no opposition.
You measure it both directions.
Yeah, well, a lot of them you can measure both directions. But if I was talking, now, of course, the only opposition we have is the tubes. The sensor itself does not measure by a pressure differential. It does not measure by a pressure. We have the sensor itself creates no pressure loss. Right? Absolutely no pressure loss. The sensor, now the tubing, we can't do away with the tubing. We can't do away with the valves that control the direction and stuff like that. But you're right. Flow doesn't matter. Well, yes, it does. Why does flow matter?
Because the current going in the
Well, no, the position of the sensing element and the magnet. So the fluid has got to flow through the magnet before it gets to the sensor. So this is measuring the difference in potential across the fluid. We induce a voltage into it, and we can't have the sensing before we have the magnetic field. So, I didn't see that, but now y'all understand that. So we can't sense it. So this guy here, you only work in one direction. The big advantage of this guy is that absolutely no pressure differential caused by the wall, caused by the sensor itself.
Is that a real? That's a diagram of one, but that's a real.
Now this is a real one right here. Yeah, well, it's 2 of them. You got to understand this would be for extremely high flow, and we should have noticed that right off the bat. It says what? It's got that arrow saying this is the direction of the flow. So if you put this in opposite, it's not going to work. It won't hurt the sensor, right? You understand
And
it?
I work with guys that would put them in back.
It's just like used to, it didn't make any difference how you put a tire on, but now they lay the threads out on the tire for what?
Yep.
For a certain direction. So every tire now has a what? Well, I'm not going to say that. My lawnmower tires don't have a direction. But automobile tires now, you got to put them on in a certain direction. Motorcycle tires too. They're designed to do what? The treads are laid out to run in one direction.
You ever seen a tweel?
Tweel.
Think about it.
So here they're showing us two different sizes. This right here might be one too. I mean, this might be a small one too. I can't tell. But these are two different sizes. So you can get these in different sizes. What determines the size of the pipe? How much flow you get. So the inside diameter determines how much flow you're trying to get, right? It's just like a conductor. The bigger the conductor is, the less resistance the conductor has, right, for the same material. Well, that's the same thing through here. But you're not going to use a big old thing like that to conduct, 5 gallons per minute, right? You understand? Because as the size of the conductor goes up, what goes up? The cost of it goes up. So these guys here come in varying sizes. So the thickness of the wall determines how much pressure it can hold in, right? And then the inside diameter determines how much resistance it would have for a certain amount of flow. These guys here would handle a lot of flow, right? This guy right here, but what you're going to choose is you're going to choose the one that is as small as you can possibly get, right, and still meet the demands that you have. These are what we call ultrasonic. Ultrasonic uses what we call Doppler effect. So we shoot a beam out, ultrasonic beam out. Depends on the sonic conductivity of a particle. Affected by temperature, density, viscosity, usable for high accuracy. So what these do is these are actually looking at the phase shift that's caused what? By a transmitted pulse and a received pulse. That makes sense? And this is the way Doppler radar works. So Doppler radar is looking at how fast something is moving, right? You understand? It also, most Dopplers also will polarize so it indicates direction. Have you ever seen them put the Doppler up there? And I don't remember which one's red and which one's green, but one of them moving one direction is red, one of them moving the other direction is green. And where those reds and greens come together, that's where we have problems, right? So time of flight, this uses the same technique. Here we're actually depending on it bouncing off. The phase shift when it bounces off the material. That's the Doppler effect. This is time of flight. Now, what do we mean by time of flight? Yeah, this is what we do. We shoot a pulse out, and then we time the amount of time it takes to what? Give up. Measures time, bidirectional flow, unaffected by temperature, density, and viscosity. This is accurate to what? About 1% of the flow. So this guy is the most accurate, but this is affected by what? Temperature, density, and viscosity, right? Okay. This guy is not affected by that, but we lose a little bit of percentage. But 1% is still not bad.
Depending on what you wanted, the material.
Yeah, how accurately you wanted it. 1% accuracy. That's not bad at all. And that's 0.001.
I wish I had that much right. Come on, Greg.
So ultrasonic and time of flight, these are both ultrasonic.
I've never seen those.
Well, maybe you have and maybe you hadn't. These guys are going to kind of look like these. So these are actually, this guy right here actually clamps on. So you have a transmitter and you have a receiver. This one is built into it. This one, if you ever seen this weird, if you ever seen these big old pipes and these weird things coming out the side at angles, right? This is either, This is either time of flight. We don't know what type this is because you notice there. I'm sorry. The Doppler will just have the sensors will be on both sides. Time of flight, they'll be on one. They'll be on both. They'll be at this angle, and that's what we're doing. So here, this is time of flight. We'd shoot it, and then we would time how long it takes to come back.
Doesn't look like it goes to the center though. Maybe it does.
Well, what they're doing here is this is really, really accurate because I don't know if you can see this. Is they're measuring the flow rate all around the tube. People don't understand where does it?
Oh, okay.
Where does most of it? So in a fluid system, your fluid is flowing fastest in the center because it doesn't see the opposition. So fluid actually flows in layers. And how fast it flows depends on how close it is to the outside or up against the wall. So the fluid up against the walls of the tubing, this is flowing slower, and the tool in the center, this is flowing faster. So what they're doing here, I guess they could do here. They could measure all three. Odds are they're taking all of them and just doing all.
So the two outboard ones would probably be the same, but.
They could be, unless we went around a curve or something like that. So if you go around a curve, the outside is going to be slower than the inside. And of course, that causes turbulent flow. This is a portable one. It looks like so. This is actually put on here. This is built in permanent. These so on a Doppler, your transmitter and receiver is going to be on the same side of the tube, right? And for a time of flight, it's going to be offset. And you can research these. I got all these, every one of these off the internet.
Okay. Quick question is the one in the upper left-hand corner is what?
This has to be a Doppler because there's no sensors on the bottom. So it's got both of this. Yeah. So you can tell the difference right off the bat. So if you've got sensors or sensing elements on both sides like this at an angle, then it's got to be a what? Time of flight. If you got it on two sides, are we okay?
Time of flight.
Yeah. So Doppler depends on reflection. Off it actually reflecting off, how much it's skewed by reflecting off the flow, right? And then time of flight actually shoots what being through the flow, and then calculates the amount of time it takes to So guys, that's all the Doppler. That's all the flow sensors that I could find. So these guys. What advantage does these guys have? Doppler and time of flight.
They don't have to be inside the front.
Well, technically, you're right, but if we don't put it in the flow, then these guys are not going to create a pressure drop, right? You understand? So neither one of these they don't create pressure drop. The only thing now we got to worry about is the tubing and also any type of valve or anything we go through. Right? Does that make sense?
Well, time of flight. It goes through.
Yeah, but it's a radio wave and it's
not, yeah, I'm with you. I'm sitting there thinking
it's an ultrasonic wave. Yeah, it's an ultrasonic wave. Yeah. It's an both these are ultrasonic. These use the high frequency right up in the ultrasonic range, sends out a pulse and then does what? One of them looks for reflection, how it reflects, how it's skewed when it reflects, right? You understand? And the other one, what? It shoots through the fluid and then looks for it to come back. And ultrasonics guys, these guys, you know, ultrasonics will travel through a lot of stuff. So, so this could be a slurry. This could be almost anything. You know, how many? Of course, they use it a lot on women that are pregnant, and that's all that is ultrasonics. And what does it do? Well, it shoots through their skin, through their muscle, and everything, right? And the density actually would give us
They use it on fat men too.
well, they use it a lot on my leg. So I went through several of them on my leg, and it paralyzed them.
Shoulders.
Yeah, which is really neat. And what's nice about ultrasonic is it's not X-ray. You know, so it's not. So when they're doing ultrasonics, they don't come in and put on a lead vest. the technician don't get behind the wall, right? You understand that? So, yeah. I'm not going to tell you. I mean, especially when I was laying on my back for over a month, they would come in there every day and take a chest X-ray to make sure I wasn't getting build up in my lungs. So guys, this is it. That's all I could find. I'm not disappointed. So this is the one we looked at. So these indicators are we're going to so what's the SI unit for flow? Now remember, flow is volume. How much volume you can move. So to calculate volume, so to calculate area is going to be something squared, right? To calculate volume is going to be something cubed. Because volume, you have to multiply the length, times the width, times the height, right? You understand? So notice we have liters, which is a volume per unit. We have cubic meters per second, right? And this is the way we abbreviate it. M3 per. So anytime you see this, we can say what? Per second. Standard cubic centimeters per minute. Standard is these standard. The problem we have with volume is a lot of times volume changes with temperature and volume changes with altitude. So if you ever looked at a compressor, its flow rate is rated in standard cubic feet per minute. What that means is that it's rated at average sea level pressure, which would be about 14.7 psi at some temperature. I can't remember the temperature. And so that's what they rated at. Now,
if it's scuba dive, the pressure.
Yeah.
You go back up, change it.
Yeah, well, yeah, and that's the same thing true in our atmosphere too. So underwater, the deeper you go, the more pressure you have. Well, same thing's true for air. So the lower you go, the more pressure you have, right? You understand? So if I was just to use something like this, then my flow rate my meter would indicate something different in Boulder, Colorado than it would down in Gulf Shores, right? But if I give a reference, then I can compensate for that because I know what it measures at sea level at this temperature, and then I know my sea level and I know my temperature, then I can compensate for that. Now, usually it's not that critical.
Right? You gave us all those charts.
Yeah. All the different. So I think you can go to just about any weather station, no matter where you're at. And one of the things they give you is that inches of mercury, right? You understand? Which would give you the barometric pressure. What you probably need to look at though is not the barometric pressure on that day. What you need to research is what we call the mean barometric pressure. So the mean barometric pressure, it's just like when they every night on the news they say it's 4 degrees above average. So that's what a mean is. The mean is an average. Because if you tried to deal with and you just live with the slight inaccuracy, right? You understand that? Because if you had to do barometric pressure basically changes what? Every day, and temperature changes every day. So what you need to know is your mean temperature for the year, and also your mean barometric pressure for the year, and that way you can compensate your indicators for that. And then you just live with what? The slight variation during the days. Because if you didn't do that, what would you have to do almost every day?
Yeah, you used to have a thermometer, and something else.
At your house?
Yeah.
Yeah, a lot of people used to buy that three unit thing, and they'd put the speed little propeller thing up on their roof. And
I guess it's in a refuge house.
might be. So these are those. So this is it, guys. This is about all we'll have time to do it. So we're not going to get into these other ones. We do, but all these are out there. So if you get into a situation where you're trying to get into thickness, all you got to do is go on the internet and type thickness sensors, right, or viscosity sensors. So we did pretty good, right? Of course, in motor controls, we learned about timers, how to measure time, right? Are we okay?
I tell you, in a mill, paper mills and stuff, you can't walk for stepping on those things.
What's that?
Sensors and
Oh, yeah.
lights and stuff. They're only point I'm making, they're heavy.
Yeah. And any automated manufacturing, anything that's automated lives off of sensors, right? You understand? Because we use our sensors all the time, but there would have to be a person out there looking when something was in a certain position, when something was something here and something there. Well, if we can turn that over to electronics, then we can process that with computers, right? You understand? Which is what these PLCs are.
Have you been down to Mercedes?
No, I haven't. Yeah. I've been to the museum down there, but I've never been in the plant. They stopped the tours. They stopped the tours for a few years while they was building the other plant, and I think they've opened it back up. But last time I checked, guys, it's like a year waiting list.
How long?
About a year.
Well, I'm curious about something. Years ago, I worked at Monster, doing design work, and I was doing the engine plant. When those engines come out, they had an assembly line. They had, I don't know how many people, but they bring the blocks in, the pistons and stuff, and different things. They bring the thing in and set the heads on there. But they had people putting the bolts in and torquing that. That's gone.
Well, yes and no. There's still some plants that do that, especially your one of the kind engines that have to be changed. Robots don't like things that change. They like things to be exactly the same. So a lot of your optional engines, like you might get on a Mustang, they have a standard engine, which is probably primarily put together by robots. But these big optional engines that they don't sell hundreds or thousands of them, then those probably are still put together by you.
These were V6s that were in the Honda Odyssey.
Yeah, but they line those things up perfectly. They put the heads on there, and you'll see these big things. They'll have the bolts already in there. They'll drop them down. They'll torque them down to the perfect torque. But you still have a lot of guys. A lot of people in there. It's just that there's not near as many. And like I said, the specialty engines, these optional engines, those are probably still put together by hand. And NASCAR engines, those are put together by hand. That always amazed me. Drag races, a lot of those guys, they'll run one run, and then they'll take that engine apart between runs and tear it down and clean it up and put it back together between runs. So
that guy down there. Your neighborhood built in fun.
Yeah. So we'll talk a little bit about what we're going to do in lab, and the problem is that there's certain labs. Well, the labs are required by the course, but we don't have to do all the labs, right? You understand? So what we're going to do is, no matter where you're at in the lab that you're in, the next lab you're going to do is you're going to go to the next lab section. So if you're on what was our first labs? Proximity sensors. And then the next lab after proximity sensors is liquid level sensor. So what I want you to do is your next lab, I want you to go to liquid level sensors and do the first lab. Everybody understand that? And once you do the first lab, then I want you to tear that down and go and do the first lab on temperature sensors. That makes sense? Okay. And then after that, now you've met the minimum requirements for the course. And then to get a real good lab grade, what can you do now? Go back and do the other. Does that make sense? We're not going to do pressure, even though we do have pressure sensors. We don't have a compressor in here. We only got one. And I left my vacuum pump. So the pressure sensors, I'll try to hook something up in that before the end of the term. The pressure sensors that we have, they're programmable, and they're really cool. But basically, instead of dealing with the generic sensor, it deals with a specific sensor. Now, the problem we have on our temperature sensors is our temperature sensors run off 24 volts DC. So what's our problem? We're using 120 volts AC, right? Y'all understand that? The temperature sensors.
Yeah, I got that. What are we gonna use?
Well, we're using 120 volts AC. So y'all go back and get one of the temperature sensors off the shelf back here.
24 volt step down?
Yes, that's what we got. So everybody go get back in one.
Oh.
Bring me one too, Mel. And then on the right hand side down the bottom, come on.
You want these, you know,
Y'all see the temperature sensor? They're blue. They got two bands on them.
yeah, don't need these power supplies.
Not right now.
Okay.
You will when you hook them up, but y'all not gonna hook them up.
Oh.
Oops.